final piece of our discussion of implementation is going to be concerned with various issues that have to do with the display, what goes up on your monitor or your panel or even your printer. So one of the things we want to do here is look at more at something we touched on way back at the beginning of the course, which has to do with our perceptual issues with respect to color. In a lot of ways, for me, this is the one of the most interesting parts of the course is our perception, how we perceive color is really very interesting, and it's been the subject of study for many years. Really starting off with photography, and a lot of research was done, and various color systems were come up with. One of the things that happens here is when you look at computer graphic systems and when you program them, basically you work in something like RGB or RGBA, and you assume, well, there is this standard RGBA, but in fact there isn't. It depends on what your sensors are, what your display technology is, and red on one system is not the same as red on another system. Likewise, if we measure color through some sort of sensors, a camera, or whatever, they're going to have different responses, and so, but we don't consider that when we do graphics. We assume it's sort of independent of any particular system, and that's been the philosophy of computer graphics. We said at the beginning a couple of times probably is that we're dealing with device-independent graphics. We don't need to know the properties of the particular devices in order to write our graphics applications. But when it comes to actually displaying the results or capturing, say, an image for a texture, it really does matter, and that's the interface we're going to be talking about today of how do we deal with colors the way we've been dealing with them with WebGL, and what do we have to know about real color systems to do this well. Well, first thing is this has to do primarily with the digital side, and just argue that that no display can be perfect. And what I'm thinking about here is that you're working in the digital world with pixels, and you're going to output an analog signal. Let's stay with the CRT, where it truly is analog. There's a value as every point as you go across. So, or you can think of something like an LED panel that has these little pixels, but your eye is merging them as if it were some sort of analog device. Well, on theoretical and practical grounds, you really can't have a perfect device, and the real way that we study this is through sampling theory, and that'll explain a lot about aliasing. But if you and I wound up putting all of that information into an appendix, because generally we don't get to it in this class, and it also requires a little bit more mathematics in this. But the ideas are the following: that if you start with discrete data and you want to produce this analog signal at the end, there are two problems. One is you have to figure out how to sort of filter this discrete data in order to have it all blend together so that you don't see distinct spots. In a way, your eye does a large part of that, because if I'm sitting further enough away, my eyes aren't perfect, so they blend together these spots. So it's a level of filtering going on that I can model, and it turns out the ideal filter that you would need as predicted by sampling theory is something that is not possible to construct. So there's always a little error in that. And by the way, everything I'm saying here about this analog digital conversion is all true with sound, and many of you, I think, are aware of that with one-dimensional signals in various music systems. The other problem is that when you display these discrete data, you have only a finite number of points, and a finite number of points is not enough to describe the entire object, which in principle could go on forever. And so there's always sort of this error, because you try to figure out or make a decision as to what to display based on only having a part of the data that describes it. The other end of this, at the front end, is when I take those samples, I actually create errors by only taking a finite number of samples, and also I have to worry about things in sampling theorem that tells me how fast I have to sample to be able to recover from the digital data. So there's no such thing as a perfect display. So keep that in the back of your minds. Although we can come reasonably close with high resolution displays and good scanning devices. Now the part we're going to focus on is this part about how we perceive color. Now we started off saying that, well, light is the part of the electromagnetic spectrum that causes our eyes and our visual systems to react. And if we measure that, it's generally somewhere in the 350 to 750 nanometer range. And a given color is a distribution of energies within this range. We know that colors that are in the middle, around 600, 650, we see as greens, and red and blues are on either end, but a real color is a mixture of all of these different frequencies. Now, what we said before is the reason that this works well is using RGB, only three colors, is because our visual system has only three types of cones, and each one is sensitive to a different region within the color or visible spectrum. And so this magic number 3 says, well, then I could reduce, in principle, the colors that on the other side to 3 primaries, which we've been talking about: red, green, and blue. They could be other primaries, and then how I convert those into the system that your eye actually uses. So the idea here is that your brain is only getting 3 tristimulus values. If I could present to you, say, a solid color, we're not worried, a very simple thing. I give you a panel with one color on it, that your brain is only seeing these 3 tristimulus values. So the model looks kind of like this. It says, well, you have a sensor, and this is true whether the sensor is one of the cones in your eyes or it's a sensor in some scanning device. You can look at it this way, that you have a little area, and light from all frequencies falls on that little area, and there's a sensitivity of that particular sensor, the cone in our eye or some other physical sensor, and its sensitivity can be described through a function S of lambda that just says, well, how much of C is really seen by that sensor. So you can think of S as varying between 0 and 1. If it's a very concentrated center in the green, for values of lambda around 350 or 750, it wouldn't see very much. And so we have 3 types of cones, each of which can be described by its own sensor curve. Now, if you have a camera that takes RGB pictures, it has its own 3 sensors at each. Think of those being in a very small area at each pixel, and they measure their own S1, S2, and S3, which are going to be different than the ones in your eye. But in terms of what goes to your eye when you see it, that essentially all of the infinite dimensional detail that's in a sea of lambda is taken out by doing this integration over by scaling by the sensitivity curve, and all you get back are T1, T2, and 3. So you can look at what the cones in your eye are doing as sort of this data reduction problem. They're reducing this function C of lambda into 3 numbers. So what 3 color theory says is that any 2 colors that produce those same 3 tristimulus values are perceived identically. The word is they're called metameric pairs, because all your eye sees is T1, T2, and T3. So you can have 2 different color distributions that produce the same T1, T2, and T3, and I can't tell the difference. And one of the ways that people see this, by the way, is that if you have people who have various types of color blindness, one explanation is that they only have 2 of the types of cones that people have. Most people have these 3 different types. And if you do these experiments, you might have seen with color wheels, and you ask a bunch of people to match the color, or say when 2 colors are the same. Most people will agree on that, but people with color blindness and who don't have 3 sensors are going to come up with and say, no, that doesn't match. So there's a lot of both theoretical and practical a lot of experiments that were done with called psychophysics literature to verify these results. So if you say, well, then what do you have to do to make two colors, to get the color you want on a display so that the human will perceive it correctly, then you say, well, I've got to produce those three tri-stimulus values with whatever display technology that I have. Well, the problem is you can't always do this. And see, this idea would say, well, you don't need to have the same primaries in your LCD panel or in your film as long as they produce the same tri-stimulus values. Well, there's a bunch of reasons that you can't do this in practice. You can do it for some colors, but not for others, and that's what makes this, what we're going to be talking about, kind of interesting. First, that if you really were to do measurements on the human curves, they're not red, green, and blue. It turns out they're blue, green, and when I say a curve is green, I mean it's centered in the green. Doesn't have sensitivity only at one frequency. It has its greatest sensitivity in the green region, and then it tails off in the blue and the red. You have sensors in your eye that are sensitive to blue and not very sensitive to green, and certainly not to red. And the third type is sort of in the green-yellow region. It isn't all the way over in the red. It's sort of halfway between, or actually it's closer to the green, but it lets in enough red that you can detect red. Now, the ones you're familiar with are obviously RGB, because that's what we're doing, but you may be getting the feeling now from what I've been saying that there are different RGBs, that you can have two different sets of sensors that each have a sensor with a concentration of red, but they're not quite the same as each other. I should mention now that, because we'll see this again later, is in print media you use the complementary colors. Because the idea with a CRT or a panel display is that you're projecting color, and so you add color to a white background. We've discussed that way back at the beginning of the course. While if you have print media, the paper absorbs white light from the outside and only reflects back some of it. And typically what's done in print media is you use the complementary colors, cyan, magenta, and yellow, or what's really done in the print industry is to use a four-color system, CMYK, where K stands for black. The reason is that when you print, and you print text, you really want that text to really be a black and be able to control that. So what they try and do is extract the blackness, so that'll come out very well, and then the remaining part, when you have colors there, think of a page that has a color picture plus a lot of black print, then the CMY that's left will let you describe that color. Okay, so the question is, how close can we come to a given color for, say, human perception when the primaries are different? And one way to do that is to look at the tri-stimulus values and see what happens when we map one set of tri-stimulus values to another set of tri-stimulus values. So let's look at it this way. You have a color, and in some system, I don't care what that is now. You can assume it's RGB if you like, or the human system. It generates tri-stimulus values T1, T2, and T3. So that's nice. It's three-dimensional. We can describe it in a little space, and we'll assume it goes between 0 and 1. The reason is that if this is additive color, then these T's have to be greater than or equal to 0. That's I think clear. But then they have a limit. If you think of a CRT that produces, say, red, you can only get a certain amount of red. You keep applying higher and higher voltages to the red gun in a CRT, you're going to blow it up. So there's a limit of how much red a sensor can put out in green and blue. So we're just going to scale that to be 0, 1. So that says for this set of tri-stimulus values, every color as perceived is a point, or generated is a point inside this color solid, and the axes are the T1, T2, and T3 axes. So the coordinates of this point, if this is an RGB system, would give us the red, green, and blue for that point, or at least the tri-stimulus values for red, green, and blue. So that's a nice way to put it, that all colors within this solid are colors that we can produce with our system. Okay, so here's, this is just looked at a little bit differently. And I think one of the reasons here I want to show you this here is these are close to the human tristimulus values, what we perceive. And here's the one that's centered in the green. This one's almost the same. It's over, well, it's over, actually, this is the one centered in the green. This one is a little bit over towards the red region. It's the green-yellow one, and this is the blue. There's a lot of very interesting things. I could talk for an hour about the blue, but I won't here. It turns out that only 8% of your sensors are blue, and so you're very much less sensitive to the magnitude of color in the blue range. It turns out you're very sensitive to little shifts within the blue range, but the brightness of blue you have very low sensitivity to, and that's a problem in a lot of design of systems. So here's where, again, the tri-stimulus values for them. Now, the T1, T2, T3 you get depend on the particular system that you're working in. So what happens if you're using some other device? Well, what I want to do is match the T1, T2, T3 in one system to the T1, T2, T3 in another system. Well, from all we've done before with transformations of XYZs, you might start recognizing, well, gee, this is exactly the same. In the T1, T2, T3 system, there's a set of basis vectors, which are the red-green, amount of red, green, and blue in that system. And I could now talk about a change in coordinate systems, because that's all you're really doing here. And so when I go from one system to another system, I can find a matrix, and those matrices are available in the standard literature. Well, a lot of this stuff goes way back, I think, to the 1930s. People were starting to get these values by actually doing measurements. A lot of it, more was done when television came about. The first people doing this were people who were doing photography. A lot was done at Kodak. And then when television came about, especially color television, we started getting other systems. And what are those systems? Well, the ones we'll talk about briefly each are NTSC, red, green, blue. That's the system that was originally derived for color CRTs in the U.S. The system, NTSC is the National Television Systems Committee, which set the standards for television in the U.S. In Europe, that's generally known as never the same color twice. But that comes not from the issue about the phosphors and the sensitivity. It has to do with the more technical aspects of how that information is encoded, and I'll touch on that in a few minutes. UVW turns out to be another NTSC system that's much better for transmission. CMYK, we said, is the standard kind of systems used in the print industry. HLS stands for U, lightness, saturation, which is a lot more perceptual. I'll come back to that one too for briefly. That was really popularized by probably HP for use in printers, and it's also in the art world. People don't think of the amount of red, green, and blue in a color. They talk about how bright is that color, its lightness, what's the name of the color, its hue, and how close is that color to being a pure color as opposed to a pastel version of it. That's called the saturation. Now, with all of these systems and all of these different ways, and there's lots of different possibilities for RGB in there, back, and I think this part goes back to the 1930s, people said, well, let's get a theoretical system where everything works. And everything working means that for every color I can produce, that the XY, that the three tri-stimulus values, X, Y, and Z, are always between 0 and 1. And you'll see some pictures of that in a while. The other thing that people started doing, and this became very important when people started dealing with color television, is to separate the brightness part, the luminance of the signal, from the color information. And the reason that came about with television is that television first was black and white. And then color televisions came along, and they said, well, we don't want to make all black and white televisions obsolete instantly when we start transmitting color, so we have to separate the color information and transmit that in sidebands. Now, in a way, people are sorry for that decision because it led to systems like NTSC RGB that are very sensitive to errors in the signal and noise and things. And maybe we would all be better off if they simply threw away the black and white televisions, which wasn't economically viable then, and just went to a better color system. But we're sort of saddled by a lot of these systems that came about because they didn't want to make black and white televisions obsolete. So first thing we do is pull out the brightness information, and then we're going to look at what's left at the end. So one way to do that is the following. Talk about the fraction of the total T1, T2, and T3. So it's sort of T1, T2, T3. The sum is sort of the brightness of the color. Not quite, because the perceptual stuff that you're more sensitive to greens and you are to reds and blues is not quite in there. But the nice thing about talking about fractions is that you only need two of the variables, because little t1, little t2, little t3 have to sum up to 1. And because they're fractions, and we said the tri-stimulus values have to be between 0 and 1, then all of the little t1, t1, t3, t3 have to be between 0 and 1. So that's kind of neat. And we get a nice 2D characterization that looks like this, is that if I say, okay, look at this surface where T1, T2, T3 equals 1. So when I go to tri-stimulus space, I'm really talking about points that lie on this triangle where the corners, if this is an RGB system, these three corners are pure red, pure green, and pure blue. And everything on the surface, it gives me the 2D picture with little t1 and little t2. So or another way to see that is if you project this triangle into little t1, little t2 space, you get a 2D picture that looks like this. T1 and T2 can go between 0 and 1. Again, they're fractions. And I can't go all the way out here, because if I look at this line T1 plus T2 equals 1, as soon as I get on the other side where it's bigger than 1, that means that somebody has to be negative. So this being in this region forces T3 to be between 0, 0, 1. So all the possible colors that I can generate are all inside of this little triangle, and that's what you always see displayed in the chromaticity diagram, or the specs for a particular printer. This is you're looking in here. So here, let's look at this. And here would be for a typical red, green, and blue space. Actually, I generated this. Really simple to write little programs that generate all of these kinds of images. You can do the color solid with the Maxwell triangle. Actually, if you look, come back here. This triangle is called the Maxwell triangle, and it goes back to Maxwell of Maxwell's equations, who turns out was very, very interested in color and color perception. But now here's the 2D picture again. So here's the red and the green, and here's the corners now correspond to total blue down here in the 0, 0. See, if they're both 0, then this is red, green, then blue must be 1. This corner is all green, and this is a pure red here. And notice you're not getting all possible colors, because these are restricted to having red plus green plus blue equals 1. So this is called a color gamut of a particular set of red, green, and blue primaries. Now, if I want other colors, the argument here is it's not necessarily producible in another system. How can I tell? Well, if I take all the T1s, T2s, and T3s for a given system, and I map it into the other system, so it's really changing to a different set of primaries, what you'll find is that in the new system, the T's are not necessarily restricted to being between 0 and 1. Some of them can be negative, and some of them can be bigger than 1. And if that's true, then you're in trouble, because you can't produce that color in this other system. So it gives you a way, knowing these little 3x3 matrices, of moving between different systems and also telling what's producible and what's not producible within that system. So here's a standard picture that you see, and this is the way that we look at it. Is the argument sort of goes like this: that suppose I just had a perfect laser for every frequency that's visible. So this would put out a This would put out a pure 750 here, a pure 725 over here. And if I plot those, I get this arc over here. So, and these are the spectral colors. And the argument then would be, if you can produce every spectral color, then you can produce any color by just adding it all together, because we're looking at a very additive model of color. But in reality, that doesn't happen. If I take something like a CRT, okay, so the blue triangle here is the CRT, and and all of this is a very linear model. So if I just map red, green, and blue, pure red, pure green, pure blue, I can make a little triangle here and say everybody else has to fall inside that I can produce on my CRT. And notice that this triangle falls inside of this arc, which says there are colors I can't produce. I can't get things out here, and I can't get things. And if you think of it physically, that makes sense. I mean, how could you take a blend of colors that's being developed by this analog device like a CRT that produces for red, actually produces a whole bunch of frequencies, and get a single red frequency out of that? You can't do that with all positive values. So that's all encapsulated in this figure. And so you can start talking about how close a given system is to what you ideally would like to have. Then you have the other problem of saying, well, what if I can produce a color on a CRT and I want to print it? Well, then I want to know what the printer gamut is. So here, the green triangle is sort of everything I can do with a given printer. And now I can look at a point like this one in the middle here and say, well, that point is producible on both the printer and on the CRT. Now I have to multiply the three-dimensional tristimulus values in one by a little 3x3 matrix to get its value in the other system. But at least I know I can produce this color on both systems. Here I have a color that I can do on the CRT, and this one on the right, but I can't get it on the printer. It's not in the printer's gamut. And I can say, well, I can come close. And I think you've all seen examples of that. One example is, and here's a color I can't produce on either. Often what happens is you'll have a device like a printer that just doesn't have the size of the color gamut of a display device like your flat panel. And then you say, well, now you're really worried about how close I can come. Now, the way these diagrams are usually drawn is to use this theoretical XYZ system. You can't physically produce this system, but it's great for references because all the spectral colors fit inside of this triangle going from 0 to 1 in X and Y, and then the Z's, we can compute the Z's from that. And so here's a theoretical system where every color has a XYZ value between 0 and 1. And so when I talk about what is red or what is a particular shade of red, or an example is, I know for fluorescent light bulbs, you used to buy them by warm white or cool white. Those are the two names. What did they correspond to? They corresponded to 2 points in the XYZ system. You could actually have sunlight here, which would be kind of a point towards the yellowish region. A pure white light would be somewhere right in the middle here. So that's the general reference system. Then if I map a given gamut onto this, I could say which colors are producible or not. So if I take my CRT gamut and I plot it onto here with its triangle, I can say, well, all of these colors I can get, and all of these I can't. Maybe this is a little too small for a real CRT, but I think you get the idea. And then I plot for a printer or that. So that's sort of the theoretical background. And let me come back to the real systems for a few minutes. So RGB is originally came from matching the phosphors in a CRT, and that's the NTSC RGB, which for a long time was the standard one that people used. CMYK, as we said, was used for printers, and actually you see that with printers because those of you who have inkjet printers, you'll notice you always have four little inks in there. You have one to get the pure black, and and 3 others to give you the colors CM, Y, and K. Usually it's translucent, the little packets, so you can see those colors. But that's why you're converting from RGB over to CMYK in order to do within the print driver. Okay, so here's again the argument about about being able. It's really just when we change color coordinate systems, we go from at least one RGB system to another RGB system, and then we'll see in a second. Here's the mapping. Just going backwards, if you want cyan, magenta, and yellow, you can just look at the complementary values. And if you want CMYK, the basic idea is that the black is the minimum of, if you go to CMY first, then you take the minimum of those three values. That's the blackness. So you extract that, and then the three remaining color values are what's left after you subtract that minimum out. The matrix that goes back and forth between them, as we said, is just to go from XYZ to NTSC RGB, or from one RGB to another RGB. Is just a 3x3 matrix that you can do. Actually, the older OpenGLs, before a lot of the functionality was deprecated, had a color matrix. So it had a texture matrix that would. So in addition to the model view matrix and the projection matrix that were stored separately and part of the present state, there was a texture matrix that was the present matrix that was used to transform texture. Okay, I had a little stoppage of Camtasia here, but I think we didn't lose anything. So let me continue on. So what I want to do now is here we can switch back and forth between RGBs. I want to just spend a minute looking at YIQ, because that's the basis of a lot of other systems, in particular television systems. So YIQ is called the NTSC transmission color system, where we said we needed to separate the color, the chromaticity information, from the luminance information. So if you have RGB sensors, and these are assumed to be the NTSC RGB sensors that correspond to the sensors in the monitor, or actually in the camera too, the brightness signal, luminance signal, is just given by taking this summation. Notice the emphasis, where essentially 60% of it is in the green range, and that's again sort of realizing that what people see is its brightness is so much dependent on the green, because that's the nature of the cones in our eye, and it's least sensitive to the blue, and the red somewhere in the middle. Okay, and the I and the Q are two values on the sides. They could have been two other values, but these are the values that were chosen by NTSC. Now, one of the problems with this is that if you start making errors, you don't get equal perceptual errors for equal errors in these components. And that's a real problem in television when you're sending things over noisy channels, and became an even more of a problem when you started looking at discrete ways and started talking about, well, I want 8 bits for Y, 8 bits for I, 8 bits for Q, which would be, kind of typical thing we do in graphics, but how a 1-bit error is interpreted differently perceptually is another thing I could talk an hour about if we had more time. So people came up with other systems to try and equalize out the errors, so that a 1-bit error was an equal error perceptually to the viewer. And the system that got used a lot in commercial television was the UVW system, which you map into from the YIQ or the NTSC RGB. The HLS system, as I mentioned, is a much more perceptual system. It's used pretty much by anybody in the art community would prefer to use that. So if you use applications, any of the applications, Adobe applications or Maya or something like that, people will tend to want to work in some sort of HLS-like system. So hue is what we would call a color. Saturation is what would distinguish, say, a pink from a red, how much white is mixed in with it. And lightness is essentially the brightness or intensity. In a way, it's a polar representation. If I look at it in terms of the color cube, you can notice, so here's the axes of red, green, how much red, green, and blue. If you take then the diagonal that goes from the origin out to 1, 1, 1 here, which would be, all the points along here have equal amounts of red, green, and blue. So all of the grays lie along this principal diagonal. So that's the least saturated colors. They don't have any hue that's visible to them at all. They all have equal amounts of red, green, and the blue. So saturation is essentially a measure of how far you are away. So if I have a particular color here in space, a point inside the solid, and I draw a line from the origin out to that color, its brightness is how far away I am from the origin, so that's the lightness of it. The saturation is how far that line is away from the diagonal, from the principal diagonal. That's a measure of S. And the hue, in a way, is how close I am to these axes. So you can think of this color, this blue line, as rotating around the principal diagonal. And as I rotate, I go from green to blue to red. And in fact, I go from green to yellow to this point over here. Down here, I'd be talking about magenta, and this would be cyan, excuse me, and yellow up here. So if, in a way, what you're trying to do is you're trying to sort of put a cone into this solid, and what's the best approximation to the cone in here. So in terms of the cone, it becomes more clear that the hue can be measured as an angle around some starting point, and as I go around 360 degrees, I go from green to cyan to blue to magenta to red to yellow back to green. And in the television literature, that you have an angle for each of those colors. The saturation is how big this circle is out here. So. And generally, that's what you restrict that to be in the range 0, 1. So you have a saturation between 0 and 1, and you have a hue, which is an angle between 0 and 360 degrees, and the lightness is how big this cone is. What's the length of that cone? So lots of things. That's just really fun literature to read. It can get very complicated when you start moving in perception. Let me finish by talking about one final thing about perception, and that's the gamma. This really combines two things. On the physical side, the intensity you see, if you look at a CRT, because that was the original way that this came up, it also turns out to be pretty close when you're talking about things like flat panels and other kinds of projective displays, that if you look at the intensity that you see, that it doesn't go up linearly with the voltage that you apply to the colors, to the color guns. In fact, it goes up with some power, gamma, and that power in a typical CRT is generally somewhere between 2.2 and 2.5, and you may want to correct for that. Now, it turns out the perceptual side is that humans correct kind of automatically, because the brightness you perceive, brightness is a perceptual quantity, how bright you think something is, doesn't go up linearly with intensity. In fact, it goes up logarithmically. So in a way, what's happening is this goes up kind of exponentially, but what you see brightness-wise goes up logarithmically, and the log and the exponential approximately cancel out. Not quite. And one of the things you can do is, for different gammas, you can use a lookup table to take in an RGB and come out with an RGB that corresponds to a different gamma, and that allows us to do some balancing for the gammas, and also make changes for if you have two systems that have different gammas. Some software for your graphics card will actually let you change the gamma, because there's tables built into the system, and most of the flat panels now have the ability to play around, let the user play around with the gamma. One of the things to note too is another problem is, what you really want on displays is to have a contrast ratio as high as you want, so you can get as blacks as you want and as brightness as you want. CRTs have a problem that they can't do a full black. There's always a little bit of gray on there, and that comes up in a lot of ways. Flat panels, because you're generating a signal from each pixel directly, don't generally have that kind of problem. But when you see in a lot of multi projector displays, the reason that because you can't get a full black, you tend to see where panels overlap because the little tiny bit of grayness you get there instead of a full black really does show up in those displays. So there's a lot of little practical things that go on. So finally, let me mention sRGB very briefly. sRGB was, I think this was done by a while ago by Microsoft and HP to get a standard for the internet. Now, there are a lot of bases. One is you want to correct for the gamma, and there were some issues that Apple monitors didn't have the same gamma as everybody else's monitors. One of them was 2.2 and the other was 2.5, and so we wanted to match that. But there was another level of complexity in that when you started doing graphics with texture mapping, now you had an image you were trying to produce, and in that image could be an image that you produced by another rendering or scanning that was a texture map. So you had this sort of double whammy happening, and in order to make things look right, what a lot of the internet stuff, you do the standard things. I think SVG automatically does this. They correct all of the colors with the gamma. So sRGB stores actually gamma corrected RG and B values, and they work out with a lot of programs, a lot of applications work out fairly well to sort of pre-gammaize the RGB to compensate for the gamma that you expect to see in your display device. It's not quite a simple linear thing. You can look this up in various ways. It tries to enhance it's a gamma conversion of just converting from one gamma to another, except for the less bright colors, so where it actually boosts them up a bit so they'll look more distinct on your display. OpenGL now has, and I think OpenGL, the new ES, has this. You can actually input sRGB colors. It will automatically convert them to RGB. Then you could apply the kind of linear processing that we're used to doing, and then it will automatically, at the end, convert everything back to sRGB. And if it's in ES, the new ES, eventually you're going to see that in WebGL. So there's a lot more to explore here, and I think you'd probably enjoy exploring some of this, but we'll stop this long lecture now.